It is truly an honor for me to introduce our next speaker, Elika Etemad, or Fantazai, as you probably know her from. So she currently works at Apple, and that's why there won't be any Q&A after this talk. But mostly what I'm sure you know Elika Fantazai for is her amazing work over the years on CSS. She's absolutely a hero of mine. I mean, I don't think we would be where we are today if it weren't for the years of work that Elika has done on so many specs.
20th year in the CSS Working Group.
20 years making CSS happen. And so for me, this is just going to be catnip for me. I am so looking forward to hearing these tales from the trenches, tales of standards. Please give a warm welcome to Elika Etemad.
Hoping I didn't break the slides in the last 2 hours. Okay. All right, imagine a world where each browser company implemented the coolest new technology they could imagine as fast as they could and shipped it in their next release for everyone to use immediately. So fast, so shiny, so exciting. This was the 90s. With each release of a browser came exciting new proprietary features like the image tag and blink, BG color, and frame, which each other browser would have to reverse engineer before they could incorporate it into their next release. The game was about creating vendor lock-in, making popular websites depend on, and therefore evangelize, your product in order to dominate the market. By the end of the decade, Microsoft was cornering Netscape on Windows and Mac. Netscape had, in a radical and unprecedented move to counter Microsoft's overwhelming resources, released their browsers open source, the first major product to do so. The W3C was trying really, really hard to get the browsers to collaborate on and implement consensus-based web standards. And a university student named Ian Hickson was creating test cases and challenging browsers to conform to the specs, finding and filing many bugs in the process. Meanwhile, web developers were getting really fed up with the situation, launching advocacy campaigns in support of standards compliance for browsers and in support of web pages that worked in any browser, not just the webmaster's favorite. By 2002, Microsoft had crushed Netscape, who was still in the throes of rewriting its layout engine, now known as Gecko, and established a dominating position with IE6, capturing well over 90% of the market. Microsoft had won the browser wars. And just as World War II left Europe littered with minefields, the browser wars of the 90s left the web platform littered with technical debt. Browser bugs, quirky APIs, and a sorry state regarding interoperability. These days, most complaints about interop are about missing features. Back then, it was straight up incompatibility on basic layouts. Web developers spent much of their development time not developing code, but working around browser differences and interpreting their code. Most web developers don't really think about where CSS comes from. Maybe CSS is defined by MDN, maybe Google invented it. We don't really care, we just use it. But most of you here know that CSS is defined at W3C by the CSS Working Group, who produces long, boring documents like this. So standardization looks like it's a slow process of drafting long, boring documents. But actually, it's kind of more often like this. Our goal is to get the specifications, implementations, test suites, and web content to all align on a single and therefore interoperable definition of what CSS is. We do this by iteratively resolving any disagreements by identifying them and crushing them. We generally try to avoid crushing the web content in this process, but everything else is a fair target. In the 2000s, the CSS Working Group turned this process towards squashing as many CSS interop bugs as we could in order to produce CSS 2.1 and browsers that aligned on it. And in the process, we learned a lot about what CSS actually is and how to write better specifications. Specifications like grid layout, which got deployed with a lot more precision than previous CSS features. At its core, standardization, at least voluntary standards like those produced at W3C, is about creating consensus on what the technology is and how it works, or at least what the technology should be and how it ought to work. And then documenting that consensus so precisely that everyone, both in the organization and outsiders, can agree on exactly what it is. The point of this is to enable interoperability, to avoid all the problems we had in the 90s with inconsistent implementations. Now you might wonder, isn't there an easier way to avoid interop problems? Like, what if we all ran a single implementation? Well, we almost got there in 2002, and it wasn't exactly utopia. For one thing, all your bugs become features, because when every implementation has the same bug, in this case, because every implementation is the same implementation, web content assumes those bugs and builds on them, and then you can't fix them later. We ran into this problem with IE6 during the CSS 2.1 era, and we still occasionally run into it today. For example, every bug having the same intrinsic sizing bug is why content sometimes overflows in auto-sized flexbox. Chrome tried to fix these cases, and that broke the web. But the other reason, and what I want to talk about today, is that the standardization process forces a type of cross-team collaboration and wide review that just leads to better quality web platform for everyone. Because people from different teams and different industries, with different perspectives and experiences and priorities, are all hammering on the same object to ensure it's strong enough to endure all that critique. So what is CSS? If we're going to define what's better CSS, we need to define first what CSS is, or at least what it tries to be. Like, what is the goal here? Okay, well, it's a style sheet language for sure. But I would say what sets CSS apart from many other publishing technologies is that rather than the designer describing the result of their design, CSS tries to express the intention of the design and then makes the browser execute the result. So now that we know what we're trying to sculpt, let's talk about hammers and chisels. If we want CSS to be awesome, we need to know what awesome CSS is. One of the core ideas of CSS Layout is that it's flexible. When Håkon designed multi-column layout, he intentionally did not guarantee that you get the exact column width and column count you specified. Instead, those numbers are the starting point of the layout, but the columns will adjust appropriately so that no matter what screen size you are on, it always looks like it was sized perfectly to fit. Web pages are often loaded in environments the author didn't expect. Maybe the window is narrower than they expected, or the expected font wasn't available, or the page got translated to French, so all the text got 20% longer. We don't want CSS layouts to be fragile. Fragility comes from expressing the result of a layout rather than its intent. When Microsoft first submitted its proposal for scroll snapping, it looked like this. These are all properties set on the scroller. Scroll snap type you might be familiar with. The other two properties were scroll snap points X and scroll snap points Y, which took lengths. This is probably, like it's a list of lengths. This is probably fine as an operating system API for application programmers, but it doesn't work for CSS. Why? Because the designer doesn't want to snap to 372 pixels because it's 372 pixels. They want to snap to it because there's something there that they want people to look at. So in the next iteration, in response to working group feedback, we added the ability to target a point on an element to a point on the scroller and snap those together. This still wasn't quite getting at the heart of the matter, and also it didn't do anything reasonable if the viewport happened to be smaller than the element. Still, since it was an appropriate starting point, the working group adopted it as an official working draft and to continue working on it, and Mozilla's Robert O'Callaghan kept pressing for improvements. The revision that made it a candidate recommendation shifted the underlying model from points to boxes. We like boxes in CSS. This reuses the concept of alignment to derive snap points from the ideal alignment of an element within the viewport. An inward scroll snap padding on the scroller allowed uniform spacing away from the edge of the viewport or masking out an area occupied by floating toolbars and defines a snap port to snap within. And an outward scroll snap margin on the element allowed per element adjustments, defining a snap area to align within the snap port. And then the snap area, if it's larger than the viewport, is allowed to pan freely as long as it's fully occupying it. One of the key principles for CSS is avoiding data loss, at least by default. If the author didn't explicitly ask you to clip the content, then make sure it's visible. It doesn't matter if the content is in memory if the user can't see it. That's why using the box alignment model was critical for scroll snapping. Sometimes the viewport is smaller than the content, and sometimes the author didn't expect that. If the browser knows it's snapping a rectangle, then it can notice that it's too big and allow the user to pan around if it overflows the viewport. You can't do that with points. Now let's talk about grid. In the early drafts of grid layout, there were properties to specify an item's position in terms of rows and columns. But what should be the default position? We considered stacking them all into the first cell, but then they'd overlap and you could only see the last one. We considered making it really obvious that the author had made an error by covering the entire explicit grid, but that also has a problem of hiding content by default. And in the end, we chose automatic placement into the next unoccupied grid cell as the default behavior, even though it was more complicated to define and implement, because that ensured the content would remain visible by default. The vision for CSS, in keeping with Tim Berners-Lee's vision for the web, has always been to enable interoperable cross-device, cross-operating system, cross-implementation pages. Making CSS work across systems is why we have font fallback instead of missing glyph tofu. Making it work across devices is why we have media rules. And it's why Apple worked on defining image set. And it's why we have PX unit. A long time ago, in a not so far away land, since this was probably also Europe, Young, Bert, and Håkon were developing the proposal that became CSS1. Back then, web browsers did not fit into pockets. Laptops were kind of clunky, and most monitors had a resolution of 70 to 90 dpi or something like that. So when software developers wrote software and designers made graphics, they defined their shapes and text in device pixels, and therefore everything scaled with the screen resolution. 640 by 480 was common, and 800 by 600 was even better because you could fit more on the screen. The default font size of the web was around 16 device pixels, which was perfectly readable on such screens. However, printers had a resolution of 300 to 600 dpi, and 16 device pixels would not be perfectly readable to most people. And so the CSS PX unit was defined not as a device pixel, like most other systems at the time, but as the whole number of device pixels that was closest approximation of the reference pixel, specifically the visual angle of a 90 dpi monitor held at arm's length, at Håkon's arm's length to be precise. This meant not only that design size in PX units would be equally readable on any device, whether a desktop monitor or a projector or a handheld or a billboard or a printout. It also meant that sizes in whole PX unit would always use whole device pixels, which is an important consideration since fractional pixel sizes generally render poorly. PX was a relative unit and a definition designed to scale across a wide variety of device resolutions, including the future of high-resolution computer screens and health millions that we are now living in. And for people who wanted to describe things in absolute terms, CSS also had a variety of absolute length units to make it easy to output absolute sizes when needed. Anyway, CSS is designed to be cross-platform because web pages need to render everywhere, on every device, on every operating system and computer architecture. You're probably familiar with CSS's forwards compatible parsing rules. Rather than choking on a syntax error such as an unsupported feature, CSS cleanly drops the portion of your style sheet that it didn't understand, allowing authors to progressively enhance or gracefully degrade their designs to work on older browsers and newer browsers simultaneously. In the CSS Working Group, we keep this in mind when defining new syntax for CSS. We also have a backwards compatibility principle, which is why CSS has levels and not versions. Newer CSS always builds on older CSS. In other words, the behavior of existing features doesn't change over time. That's why the .style object always returns the shortest, most backwards compatible syntax and not the currently shortest possible syntax. And it's why we never fix the missing hyphen and no wrapper current color. Then there's the principle of web compatibility. If the web assumes some behavior, even if that assumption is wrong, and breaking that assumption means web pages render brokenly, we adopt that assumption into the specs. Story time. So as we mentioned, CSS has this amazingly expressive menu of units. The visually relative PX unit, the physically relative absolute units, as well as the font relative units and percentage relative units that you are all undoubtedly familiar with. However, this clever system ran into an impassable roadblock. Ever since the first implementation of CSS in IE3, implementations had made a very simple and, given the non-variety of devices at the time, very pragmatic assumption. An assumption that web developers also assumed and coded their web pages against. An assumption that became embedded so deeply and so pervasively within the fundamental math of the web that it simply could not be broken, as Mozilla discovered when they implemented proper calibration on higher resolution devices in 2010. If authors are assuming that 12 point equals 16 px, and there are 70 pt in an inch, then since 1 inch is equal to 2.54 centimeters, which is equal to 254 millimeters, 254 millimeters has to be 96 px. And if you can't change the relationship of a px to a millimeter because you can't break this equation chain, and you can't change the definition of a px unit because it really does need to continue rendering as one device pixel on a typical computer monitor, well, then you just need to redefine the millimeter, which is exactly what we did. Or more precisely, we defined that 96 px is 254 mm, and one of these two, depending on the device, with screens using px and print using mm, would be the anchor unit that defines all the others. So at least when you print, 1 mm can be 1 mm, but you know. That debate about what we should and about what we could do to possibly avoid it was probably the second largest discussion thread on the working group's mailing list. Because redefining the millimeter is not really within our purview, and we also didn't really want to reduce the fidelity of CSS's unit system. But we couldn't ship the originally specified behavior. Browsers just can't break the web. To design a system that is robust and flexible, that can effectively represent the intent of the designer, we do need CSS to be powerful enough to express those intents. CSS gets a lot of expressive power from simple things like the plethora of units, or the clever multi-column interpretations we looked at earlier. But it's really with Flexbox and Grid that we start to see CSS flex its power to describe complex layouts. You can take this famous poster, for example. What does it mean to make it responsive? Even print designs have intents underneath them, and with the power of the track sizing functions in Grid Layout, CSS can express the underlying relationships of different design elements to each other, and thereby make a layout such as this respond to the available space in a way that honors the design's intentions. But power is useless if nobody can figure out how to use it. So, although a long-standing principle in CSS is to make it understandable. CSS1 described itself as a simple style sheet mechanism that allows authors and readers to attach style to HTML documents. And moreover, the CSS1 language is human readable and writable. We've come a long way from simple, but it's still very much a goal to make CSS as humanly understandable as possible. And while CSS altogether might not be simple, and the designs people are building these days are certainly not very simple, if you're trying to do something simple, it should be simple to do and simple to understand. In fact, we want to make CSS easy. Yes, we want the simple things to be simple, we want the complex things to be both possible and understandable, and we also want there to be a continuity between the two. So you can start with something simple and add on to the complexity that you need. We do this with SmartDefaulting. Ever notice that from a totally unstyled Flex container, a lot of layouts are only one declaration away? That was entirely intentional. We could have made the default fully inflexible or fully flexible, and we almost did. But we made it semi-flexible on purpose to put the most common layouts within easy reach. We do it with the auto keyword, which hides a lot of complexity involved in doing the right thing, and also lets you switch away from it to a more specific other thing. We do it with ShortHands, which can reset a whole set of longhand properties at once behind the scenes, whether you're thinking about them or not, so that you can focus on the effect you're trying to create. Or connect together, or let you connect together in a more understandable way the properties that you're setting in a kind of coordinated way. And we work really hard to find keywords that can express the common concepts so authors can think in desired effects instead of in coordinate math. We also let you reorder arguments whatever you can so that it's not necessary to memorize the argument positions, and we make as many things as possible plus optional. There are some really cool layout algorithms out there that can solve all kinds of fun and interesting constraints, but we can't always use them because CSS needs to be performant. Because when you're loading a web page in incremental pieces over a slow connection, or JavaScript is doing acrobatics with the DOM, or some developer wanted to load up hundreds of megabytes of log files in the browser, users still expect the browser to respond quickly. So browsers use the dumbest line-breaking algorithm by default, and grid layout only does 2 cycles to check if there's a row column size dependency on some items, which gets it right most of the time, but not always. And in some circumstances, percentages just fall back to auto. One of the main debates over the design of the new masonry layout feature that Nicole Sullivan will be presenting tomorrow is performance considerations. Where do the various features interaction to create performance problems What is the true nature of those problems? And how can we resolve them, or do we have to disallow them? Over the next few months, we'll be debating these issues, so stay tuned to find out. The web is worldwide. And so over the years, we've improved support for non-European languages. CSS2 added better support to right-to-left text. And for CSS3, the working group planned out improved support for non-writing Western writing systems like Chinese and Arabic. The initial drafts of what was then called CSS3 text hadn't really considered what happens when you mix the two, because that was generally something people did a lot. But the web integrates the whole world. So if you're in China teaching Arabic or in Arabia teaching Chinese, that also needs to work correctly. Which brings me to my next point. CSS is an integrated system. It isn't like NPM, where every module lives its own world, creates its own set of conventions, and only worries about itself. Every part of CSS integrates with every other part of CSS. And one of the biggest challenges in the working group is trying to keep it all hanging together as a single coherent system. Even if a feature doesn't explicitly interact with another feature, we want consistency in their syntax patterns and behavior whenever an analogous situation applies, so that authors can reuse the knowledge they have and learn new areas with minimal effort. So as I mentioned, in scroll snapping, even though we needed to add a none keyword, we reused the concept and the syntax of the box alignment properties. We reused the concepts and syntax of margin and padding. And because the resulting effects had usefulness outside of scroll snapping, we extended these properties to apply not just when snapping, but anytime the element is brought into view by the user agent, whether through user interaction such as tap to focus, or through a JS API such as scroll into view. And so actually the final version of scroll snapping that shipped didn't include scroll snap padding or scroll snap margin, because we renamed them to scroll padding and scroll margin to reflect their more general role. This is the syntax from the first official W3C draft of CSS grid layout. It combines several things: Microsoft's track-based grid proposal, BERT's ASCII art template layouts proposal, an auto-position extension of the Microsoft proposal, and the ability to name lines and to position by start and end lines rather than track numbers. But the combinations were merely additive. There were some conflicts, like what if you specified an end line and a span and a template slot? And it wasn't very well integrated with the rest of CSS. So along the way to the ultimate grid specification, we switched to using existing properties for existing concepts, like z-index, item alignment, and gaps. We worked on integrating existing properties that didn't apply in the first draft, such as applying the content alignment properties from Flexbox to apply to the grid tracks. That required figuring out an interpretation for stretch. So for stretch, we changed the definition of auto track sizing to absorb any extra space after track sizing was done, and that made auto track stretchy. And we made that the default, just like in Flexbox. We also incorporated the min width and min height properties, using those minimums instead of the min content always as a minimum, as in the early drafts. This allows the author to override the minimum of an item to something else using min width or min height. We extended the grid properties to apply to absolute position elements with grid as their containing block, so that 0 insets reference the specified grid area instead of the entire container's padding edge. And finally, we integrated within grid itself, going from a collection of uncoordinated properties that sometimes conflict with each other to the more coherent system that we have today. So, this is what it means for CSS to be awesome. And if we could sum up what the CSS Working Group does, is it takes a pile of problems and ideas and processes them into a style sheet language that allows the intent of the designer to be communicated to a browser that execute on that intent flexibly, robustly, powerfully, understandably, performantly, compatibly, across all platforms, devices, languages, and writing systems. In other words, across the whole World Wide Web. Okay, we have a mission. Now how do we actually get there? How do we go from a collection of problems and ideas to really awesome CSS? This is the original CSS2 definition of margin collapsing. This is the CSS 2.1 definition of margin collapsing. It is 4 times as long. In addition to the basic area cases covered in CSS 2.0, it also defines the interaction with floats, clearance, height, min height, line boxes, max height, white space collapsion, absolute position descendants, overflow, inline blocks, and various other cases that the original definition didn't take into consideration. The ambiguities in the original definition were the source of many differences in behavior that web developers had to engineer around, and CSS2 was full of such ambiguities. It took the CSS Working Group the better part of a decade to trawl through them all. These days, we try to do better up front. Okay, but margin collapsing is hard. How about we look at something easy? Something like border radius. We could totally define border radius in one paragraph, right? Okay, well, we should have an image and an example. That's nice too, right? Okay. And I suppose we have to explain how the different values are assigned to corners. And what if the different sides of the border are different widths? What if the border radius is smaller than the width of the border? We have to like say what you do there. And then things get kind of weird when the outer radius is larger than the inner size. So how do we handle that? Do we like make it shorter? What do you do? It seems obvious, but it also does need to be said that the background gets clipped to the curve. And also when you apply overflow, the content gets clipped not to the border curve, but to the inner content edge curve. And then we also have to say that clipping affects region sensitive to mouse events. Then there's the question of where does the color change if each side has a different color border. We don't want it halfway through the curve because then if you transition from a thick border to a zero border, it gets cuts off kind of weirdly. And then we've got, what if the radii are intersect or are larger than the box? Well, we added an example here because it's kind of weird. There were multiple options we considered here, allowing random sharp corners in the sides of the middle of the sides, or reducing just the affected radii, but we went with the option that does the best job of preserving the overall shape of the box, which is to reduce all of the radii by the same factor. Unless we have to say what happens in tables. Okay, that's border radius. Working through all these details is important, not just for interop, but so that we can get good behavior. With CSS2, we had to react to what got deployed, but with newer specs, we have an opportunity to figure out what behavior should be before browsers go out and ship it. And that means being thorough. I've often thought that one of the great things about Mozilla engineers is that they let us know when we're wrong. For a while there, I would say that they were the best at it. Where many browser engineers would just implement a spec and like as best they could, Mozilla engineers and their QA volunteers would file issues. This bit of your spec is ambiguous. It doesn't cover this case. It could be interpreted multiple ways. Let's get a resolution. This bit doesn't make sense. It should be saying this other thing instead. Pretty sure it should say this other thing. This feature is poorly designed in these ways. Let's do better. That's how we got scroll snap to where it is. This bit conflicts with browsers have implemented, and we need to decide what's the correct behavior, the browsers or the spec. It's through these kinds of issues that we were able to improve the specs. But there are many ways of being helpful. When Melinda Grant was HP's rep, she would often interrupt a conversation with profuse apologies about not understanding, but could someone please explain X? And it was inevitably that missing explanation that helped the conversation move along in the right direction. And Steve Zillis from Adobe would occasionally pause the conversation to summarize where we're at, which helped us all move forward from a shared common understanding and stop repeating at each other. In my case, volunteering to take minutes not only meant that we had better transcripts of our meetings to refer to, it meant that I was paying much deeper attention to conversations I didn't quite understand, which then led the ability to contribute later. And it's not just browser engineers and working group members. Many of the fixes to CSS 2.1 were suggested by members of Mozilla's QA community. Multiple refinements to anchor positioning were the result of feedback from early experimentation by authors like Roman Komarov, who sent feedback on things he thought were needed to work better. The new viewport units came out of an issue filed by Anthony Frenner, who not only wrote up a clear overview of the intractable problems that authors were running into on mobile, but shepherded the following discussion as it developed a final proposal. And the slider track and slider thumb pseudo elements benefited hugely from Sarah Sweden's fantastically thorough analysis of use cases and the pros and cons of possible solutions. Multiple core members of the CSS Working Group started out by simply working on problems that were in their way. Getting involved in areas that aren't our core expertise or our employer's top priority is how we keep the quality of the web platform high. Whether by helping to organize the discussion or suggesting changes, drafting an analysis of a problem, or even just asking for clarifications, we get more eyes on each development in the web platform and better decisions and designs and specs as a result. Sometime before I joined the working group, they issued a last call for comments on what was then called CSS 3 text. Lacking any knowledge about internationalization or typesetting, I figured the only thing I could contribute would be copy editing. But as I carefully read through the spec, I had a lot of questions. What if you miss Arabic into your vertical Chinese? It doesn't seem like it would render correctly. Why have 3 properties to control whitespace that have 60 possible combinations, most of which are useless? Couldn't there be a better way to do this? Have we considered how often this auto-detection heuristic would give the wrong result? Maybe we can do something smarter. These questions eventually led to the research and development of what became the writing modes and text specifications, which tried to answer all of those questions, and enable support not just for each writing system individually, but for combinations of any of them. This work happening in CSS even led to changes and additions in upstream technologies like Unicode and OpenType. Sometimes it takes a while to get to the right answer. On the 15th of October 2001, W3C released a recommendation defining a technology called XSLFO that probably nobody here ever heard about. But unlike CSS, it had logical, and by which I mean writing mode relative, variants of all the directional properties like padding and margin. They were named start, before, after, and end, and CSS almost copied the naming scheme for its own logical properties. But while it was obvious which side of a particular axis each term belonged to, it wasn't as obvious which axis it belonged to. As a spec editor out of ideas, I raised the question at multiple meetings trying to encourage people to suggest some better names, until finally we had a solution. Just use start and end in both axes, and prefix them with the name of the axis. Like this. And we got these super cool bonus shorthands out of it too. Using the same word keywords in both axes let us use simple, consistent syntax where the axis is already ambiguous, like the alignment properties. Unfortunately, we kind of screwed up on the alignment property names. It would have been nice if we figured out this pattern earlier. When Microsoft reassembled its Internet Explorer team to work on IE7, they were under a lot of pressure from advocates and from the Standards Compliance Alliance of the other browser engines. So naturally, they sent reps to the CSS Working Group to participate in the development of these standards. At the time, the CSS Working Group was slogging through CSS 2.1 issues, deciding for each issue which was the correct behavior based on a combination of what made sense and what was web compatible. With Microsoft MIA, having disbanded the IE team after the release of IE6, many issues came down to, what is IE6 doing? Because with the level of market capture IE had at the time, the most web-compatible behavior would be whatever IE6 is doing, whether or not it was the most reasonable answer. After Microsoft rejoined, I distinctly remember for one table layout issue, the group was about to resign itself to copying IE6 when Microsoft's rep, Marcus Milke, spoke up and said, more or less, actually what IE6 is doing is kind of stupid, and we'd rather copy Firefox. You could say that was the moment when Microsoft went from being the dungeon master to being a player in a joint quest to defeat IE6. It would have been easy for Marcus to say, yeah, let's make the spec match IE6. It would have been less work for his team, but it wouldn't have been better for the web. And we're very lucky because we see this pattern over and over in the CSS Working Group. The reps from the browser vendors are trying their best to make their best decisions for the web. We may have disagreements on what the best decision is, but we're all trying to work towards the greater common good. And that gets us both better specs and a more effective cross-organizational team. Most of the major proposals in the CSS Working Group are synthesized from the work of multiple teams and individuals, each bringing their own strengths and contributions to the table. Let's look at grid. This is the syntax from the first public working group of CSS3 Advanced Layout, Bert's proposal for a grid layout system in CSS. You can notice some familiar things, such as the named area string template. This is the syntax from the first editor's draft of CSS3 grid layout, Microsoft's proposal for a grid layout system in CSS. Microsoft's proposal has a very programmatic syntax with tracks and span numbers. And here we have the actual CSS grid syntax. It combines features from both BERT and Microsoft proposals, as well as numerous improvements developed along the way, some of which you saw earlier. We incorporated BERT's ability to represent complex ideas in simple, user-friendly syntax. We incorporated Microsoft's powerful track size expressions. We got their numeric tracks and spans model for a lot of use cases that do need it. And we adopted a line-based model at this instance of Adobe and HP because of their experience with graphic design, and allowed the use of line names to make them more understandable. The final specification, which combined all these ideas together in an integrated way, resulted from the sustained collaboration of layout engineers, spec editors, the rest of the CSS Working Group, and everyone else who commented on early drafts. One of the constraints of the web platform is that we can very rarely, almost never, correct the mistakes of the past. There's no version 2 that everyone can upgrade to, and there's just an ever-increasing API surface that we can expand. The future is long, and the developers using CSS are many, so we have to step up and always do our best as the CSS Working Group. When Google started to work on anchor positioning, the working group was excited because this was a problem that clearly needed solving. Google put in a lot of work to draft a spec and prototype and implementation, and after hammering on it for a couple years, concluded that they were done and suggested that it was time to ship. Apple's reps took a closer look and concluded that while it solved the problem, it didn't solve it delightfully. Common relays required a bunch of non-obvious calc math, the fallback position list had multiple forms of implicit magic that combined in a way that was really hard to follow, and it didn't integrate with the cascade properly. Simple things just weren't all that simple in how they were expressed. It was powerful, but it wasn't easy and it wasn't well integrated. So we sketched out a counter proposal. Not because we wanted to replace the existing proposal exactly, but to show that there was room for improvement and what that improvement could look like. Because as with grid layout, the ideal solution was probably in the integration of the two approaches. And over the course of the past year, through collaboration between Apple and Google and the rest of the working group, the anchor positioning spec has shifted to a much more delightful system than it is today, which Chab is going to show you in his upcoming presentation. My point here is we shouldn't solve for it solves the problem. We need to strive for it solves the problem excellently. The CSS we create shouldn't be exciting to web developers when it's new just because it addresses a frustrating problem at all. It should solve it so well that even 5 years later, it's still a delight to use and supports designers in building creative, robust designs rather than just merely enabling them with lots of hard work. I mean, you already put a lot of hard work, but we should make it a little easier. Because we are constrained by web compatibility, the bar for improving or removing CSS features is almost impossibly high. So our standards for things we need to add needs to be correspondingly high. This is how we can get a working group that produces awesome CSS. Awesome CSS like grid. So the purpose of the CSS working group is to collaboratively process issues and ideas to improve CSS through its design principles into a style sheet language that is flexible, robust, cross-platform, compatible, powerful, understandable, performant, worldwide, and a delight to use. And you can help us get there by commenting on experimental work and holding us and the browser vendors to this standard. Thank you.